getting started. Okay, so we'll get started. So today's speaker is Dennis Perepelitsa. So Dennis got his PhD at Columbia University with the Phoenix experiment. Afterwards, he was a postdoc at Brookhaven before joining the Colorado Boulder physics faculty in 2016. He's a member of both the Atlas experiment at the LHC and S Phoenix that should be coming to Rick in a few years. So we're happy to have him joining us here today. I think he's going to speak about his work on collectivity and the LHC collisions. So thank you, Dennis, and I will pass it over to you.
Okay. Yeah, thank you very much, Nikki, for the introduction. Yeah, nice for me to be back at the Heavy INT seminar virtually, I suppose, this time around, but hopefully back in person in the near future. Yes, so my talk is really aimed at trying to see, the original motivation is really to see how can we make the collective behavior in these small systems at the LHC turn off? How can we actually make them stop? So is there some extreme regime for particles that have a very large mass, particles of very high PT, ones that are arising from jet fragmentation, or looking at very exotic small systems where we can start to delineate a boundary between what flows and what doesn't. And so Nikki, you mentioned this is, I'm going to talk about my work on collectivity LHC. I actually want to stress that even though I'm the one giving the seminar, I'm representing the work of a lot of young people in the University of Colorado experimental nuclear physics group. So I'm going to try to highlight some of their faces as you see throughout the measurements. Up above, here are some nice photos of us in the pre-pandemic times when it was okay to be close to another human being. And then we sort of have been making do, during the pandemic. Here's a socially distanced version of a group gathering.
Whose backyard?
That's Jamie's backyard.
Cool.
Yeah. All right, good. So let me go ahead and get started. So the orienting scientific question that all these measurements are trying to answer is, we're trying to understand the nature of the QCD system formed in small collision systems, so in PP or PA collisions. And our starting point is the collective behavior that we've observed now in many different ways in these systems. So we see in a pretty broad and robust set of measurements that low PT particles, the so-called bulk particles, move in a collective way that we measure. So what's shown here, this is kind of a summary set of plots of the azimuthal anisotropy coefficients. So the V2, the V3, the V4. And the different panels here show you different collision systems. So proton-proton collisions on the left, proton-lead collisions in the middle, lead-lead collisions there on the right. We see a very clear non-zero values for the V2, the V3, the V4 as a function of PT in all of these systems. And perhaps what's more impressive to me is we have what seems to be a pretty global description of these phenomena in terms of final state interactions that partons are participating in the evolving QGP medium. And the colored bands that you see there, those are the results of a single hydrodynamic calculation with sort of fixed parameters. It's not tuned individually system by system, which really seem to reproduce quantitatively the azimuthal anisotropies we see here. So in the PP and PA and AA. And so, we have a broadly successful description of this kind of phenomena in PA and even high multiplicity PP, all within the same AA-like hydrodynamic framework based on final state interactions. And that picture, I would say, is corroborated by a broad set of supporting evidence, okay? Evidence for the hydrodynamic paradigm. Evidence such as, so one can perform projectile scan at RIC, where one collides protons on nuclei, deuterons on nuclei, tritons on nuclei, right? These are collisions which have different intrinsic second order and third order geometric eccentricity. And if we do that set of measurements, we see that the hydrodynamics very faithfully translates those into a set of V2 and V3 values, which are different in the way that you expect between the systems. So that's sort of very strong evidence that corroborates this hydrodynamic picture. We see that, for example, if you measure the V2 for identified particles, so particles where we know what the mass is, the V2 trends have a particular mass ordering, which is what you would expect if they were moving in a common fluid velocity. There's an example of that from Phoenix here on the bottom right. And there's other evidence, for example, from multi-particle correlations, where you could really tell that it's particles moving in a global sort of fluid field. It's not just some spurious correlation between particle pairs, but it's really describing a global phenomenon. Okay. And so looking at this successful paradigm, the successful picture, what we set out to do in the following series of measurements is basically to try to make that paradigm break, okay? To basically push these measurements of collective behavior into new regimes where, boy, you'd think hydrodynamics would have a hard time describing the phenomena there, or you really think you would see the collective behavior turn off. So what are we going to do? So I've been talking about signatures of collective behavior pretty broadly. Actually, for this talk, I'm only going to focus on the signature, which is azimuthal anisotropies in the transverse plane. And our goal is going to be to try to delineate the boundaries of where we observe versus don't observe collective effects. So is there some line in the sand we can draw by which these azimuthal anisotropies go to zero, they turn off. And the idea is that if we can find where that boundary is, that might really tell us something about the underlying physics mechanisms of what is responsible for the collective motion, what combination of initial and final state effects. Okay, good. So I'm going to show you three measurements. The first one is a measurement of the behavior of high PT particles, very high PT particles actually, in proton-lead collisions. This is a measurement that was led by a recent PhD graduate student, Kurt Hill, who's pictured there in the upper right. So he got his PhD, I think, just about a year ago. And actually, Kurt ended up winning one of the Atlas Thesis Awards for this paper, plus another one that he led. And Kurt is now working for a self-flying plane startup, I think in Oakland. So he's probably much closer to where most of you are geographically than where I am in Colorado. Okay, so high PT particles in P-lead collisions. So maybe let me step back a second. So a broader question is, given the collective behavior that we see in the soft sector, it's natural to ask, what should we expect to see in the hard sector? And this is a problem that certainly people have been thinking about from the perspective of theory. Here is a plot from a very nice calculation by my colleague at Colorado, Paul Ramachka. And what Paul does is he has the same model of the QGP fluid that of a size and temperature and lifetime that one might expect in proton nucleus collisions. And he calculates the azimuthal anisotropy under two different limiting regimes. First, under a many scatterings, a hydrodynamic regime that's appropriate for low PT particles. And so he produces a value of a V2, V3, V4 that you see there in the hatched bands in different colors. And then he also does the calculation in a few scatterings, or an aromatic, it's sort of the opposite of hydrodynamic regime for very high PT particles. And he gets the colored bands that you see there on the high end, the dark red, blue, and yellow. And then he sort of interpolates, those are the dashed black lines, interpolating kind of by hand his calculation in the many scatterings and few scatterings regimes. And so basically, one conclusion of Paul's work here is that if you have final state interactions in the system, then those should result in azimuthal anisotropy both at the very low end and also at the very high end, right? That the two sort of go together. Low PT and high PT particles are moving through the same physical medium, and so it's very natural that you can't have one without the other. Okay, so given that motivation, people have certainly looked for for what's happening for high PT particles in the first proton-led data at the LHC. So the plot that you see on the left, this is actually from the earlier run 1 5 TV proton-led data. And what you see reported there is the V2 in black, the V3 in red, the V4 in blue, and as a function of PT. And what you can see is that the V2 really doesn't seem to be falling to 0 very fast. So even in this early data, kind of limited by statistics, there's some evidence that perhaps a finite V2 persists out to 10 GeV or so. Now, these measurements are made with extremely high multiplicity p-lead selection. So I think the n-charged ranges I'm showing you here are something like the top 0 to 1% of the data. So you might of course have that skeptical question in the back of your mind. Maybe this is some ultra rare phenomenon, but it's not broadly relevant for p-lead collisions as a whole. It's fine. But nevertheless, this is pretty interesting because a high PTV2, certainly in the AA collision systems, there's an example of the V2 in black in lead-lead collisions on the right. We understand that as arising from a rather different physics mechanism. We really think of a high PTV2 as arising from jet quenching, from a differential energy loss in plane versus out of plane. So it's very interesting to possibly observe this kind of thing in the proton-lead data. Okay. Now, with the 2013 proton-lead data, we couldn't do much more than this, and so it was really Kurt who pushed this analysis using a high statistics 2016 p-lead data and some technical improvements, I should say, to really measure the high PT region. So maybe I'll just briefly mention that technically how these measurements are done. So these are two-particle correlation measurements. So one reports the delta phi distribution between two particles, which are separated in pseudorapidity. Okay, separating the particles in pseudorapidity cuts down on a lot of what's known as the non-flow. These are correlations in that delta phi distribution, which would arise from particles that are nearby in a fragmenting jet and things like that. And so one needs to that delta eta separation removes a lot of this effect, but one needs something additional to remove the remaining non-flow component, as it's called. And in Atlas, we do this with what's called a template fit. Basically, we peg the shape of the non-flow contribution from lower multiplicity data, and then we sort of scale and subtract it, and we recover the underlying modulation if there is any. Okay, so this is a standard procedure in Atlas. We've used it in a number of other analyses. People can ask me questions about that if they like. So let's see. So since high PT particles, we know they come from jets, we actually use jet triggered events to give us a large yield of these, so we can check if they're modulated in an azimuthal angle. And it turns out that if you use jet triggered events, actually the non-flow is large. You have to devise some additional techniques to reject it. So we actually, the trigger particle is a high PT one, but for the associated particle, we require it to be separated from any jets in the event. And you see if we do that, then these delta phi distributions look a lot closer to sort of what you would want to extract any true ridge cosine 2 delta phi signal, and the remaining non-flow is very small. Okay, so if I go to my next slide here, here are two examples of these delta phi.
That's a question?
Yeah, a question.
Go back to the previous. Yeah, I may have not completely following, but requiring associated particles to be separated from any calorimeter jets, isn't that a bias in the sense of an anti-bias? If you have in some intermediate PT, if the ensemble average population is 20 or 30% coming from what you would call a calorimeter jet, you're sort of biasing against that population. Can you kind of give a little intuition why this is a good kind of thing to do and doesn't introduce a bias?
Sure. So I would say if the phenomenon you're searching for is a global azimuthal modulation of all the particles in a common velocity field, then it frankly doesn't matter. It doesn't much matter what you correlate with. You just want to make sure you correlate with a set of particles where most of them are coming from the bulk, and not from the fragmentation of a jet, which might give you these funny signals in the delta phi that are kind of hard to disentangle. But actually, Peter, maybe towards the end of this section, exactly what you asked is something we were concerned about. Is can one understand what the origin of these particles are, and can one try to somehow schematically decompose the origin of these as coming from bulk processes versus jetty processes, and is that going to affect the results somehow? So let me come back to that towards the end.
Okay, thanks.
Okay, good. So on my next slide here, let me show you two examples of what these correlation functions look like for high PT particles and these jet-triggered events with this jet rejection scheme. So here they are. So the plot on the left is sort of 11 to 16 GeV particles. The plot on the right is actually 16 to 100 GeV, all integrated together, just to give us some good statistics for this check. What you're seeing in the top panels, it's a little busy, but it's the result of this template fit process where one models the correlation function as the non-flow away side peak that we see in lower multiplicity events plus an underlying cos2 delta phi modulation, which you see there in the blue. And so the bottom panels here are really showing you that's the resulting modulation after this non-flow subtraction. So that's really that's the flow signal that we're extracting. And I thought it was nice that actually even of these very high PT particles, even though there's this significant non-flow, you really can by eye see a visible near side peak, and that we really think is the clear indication of the symmetric ridge in these events. Okay, so then using the standard methods, we can take these template fits, we can turn the results into a V2 and a V3. So the plot on the left summarizes the V2 as a function of the particle PT. The different colors there show you the V2 as it's measured in different types of events. So the black is just minimum bias events. You can see we're able to go out to 10 or 20 GeV, but the statistics fall off. And then it's really this trick of using the jet triggered events there in orange that allow us to dramatically increase the high PT range where we can measure these anisotropies. And lo and behold, we see that the V2 is finite, and it's sort of on the order of 2 to 3%, all the way out to 50 GeV. Okay, so we've blown far past that little indication in high multiplicity events that maybe it's not quite going to 0 at 10. We really see it persist very clearly out to 50. You'll notice there's a difference in the particular PT dependence of the minimum bias versus jet triggered events that's similar to what Peter was asking me about. I'll talk about that in a few slides. We also have a measurement on the right of the V3. Here it's harder to make as precise of a measurement, but perhaps the V3 is persisting to the 1 or 2% level, let's say, out to 10 GeV. So that's interesting as well. Those early results I showed you in the 2013 data were in something like 0 to 1% proton-led events. What we have done is make sure the signal is robust in a number of ways. So on the plot on the left, I'm showing you the V2 magnitude in a high PT range, but now as a function of the P-led centrality or activity classes, if you will. And basically you can see that there's no evidence for very strong multiplicity dependence here. The V2 really seems to persist over a pretty large fraction of proton-led events, no longer just the top 1%. We've also done some work in verifying that the results are compatible with a single overall global modulation of all the particles. So in these two particle correlations, one could ask, is there some particular two particle correlation source you're not accounting for? And so maybe it's a bit technical, but what people do is they do a factorization test where you vary the PT of the associated particle and you proceed with the decomposition and you see if you get compatible results. And we see that broadly, yes, we really do. No matter what the associated particle PT range is, we extract a very similar PT for the first particle. And so we really can interpret this globally as this overall single particle V2. let's see. We've also studied the underlying, what we think might be a process dependence to the azimuthal anisotropy. So this is maybe similar to what Peter was asking about. What we've tried to do is one can't do it unambiguously in QCD, but we can kind of do it schematically. We can look at each event, we can find the two leading jets, and we can statically decompose the particles in those events statistically based on those that are produced by the bulk, that they're sort of isotropic in the event, versus the ones that are coming from the jet fragmentation. They're more aligned with the leading and the subleading hemispheres. And what's plotted on the left here is us trying to characterize these different events as a function of particle PT. What fraction of them are coming from the bulk? What fraction are really sort of produced isotropically versus what fraction are associated with the jets? And so lo and behold, at low PT, most are coming from the bulk. At high PT, most particles are from the result of jet fragmentation. Perhaps not surprising in proton-lead collisions like this. And there's an interesting phenomenon where that turnover from the bulk-dominated, to the jet-dominated happens a little bit later in PT if one looks at minimum bias events there in gray compared to the jet-triggered events there in the orange and the blue. And we think that's what might be responsible for the different PT dependence of the V2 that we observe for the minimum bias triggers there in black compared to the jet triggers there in orange. Basically, the bulk particles and the jet fragments, they both flow, or they both exhibit an azimuthal anisotropy, but the magnitude's a bit different depending on what the origin is. So that's kind of an interesting hint as to that difference there. Okay, good, let me step forward. So I mentioned one motivation here was to compare with lead-lead, so we can do just that. Here is a plot where I take the V2 for these high PT particles in proton-lead events there in black and in orange. I scale them up just to be able to compare the shape to the V2 versus PT that we observe in lead-lead collisions there in green, okay? 20 to 30% lead-lead collisions there in green. And you know, if you compare, they don't match in detail, but actually they have a very similar overall rise at low PT, a fall kind of in some intermediate PT region, which is a bit different in the mid-bias versus the jet-triggered, and then they seem to sort of arrive or asymptote at a similar value in the high P region. So this is pretty remarkable because, of course, as I mentioned earlier, in lead-lead collisions, this high PT V2, we really think of that as arising from jet quenching. Yeah. So a natural question is, how do we understand these results with this very high PT in energy loss models, right? In most models with final state interactions, you have to have both at the same time. You can't have a high PT flow without a high PT jet.
Dennis, can you go back to slide?
Yeah.
I have a question about that.
Oh, yeah.
You say the remarkably similar PT dependence, but actually they look pretty different to me, right? Because in lead from, even from 10 GeV onwards, it continues to fall. Whereas in the P-lead, it looks to me like it plateaus at 10 GeV and above.
You're looking at sort of this very high region here.
Yes, where it's really doesn't have any V2 at all.
Yeah, I suppose with uncertainties, it's okay. One could check what's the origin of the uncertainties on the lead. Is it really consistent with it, with it falling?
Yeah, I would say fit a slope. You've got the error bars,
Yeah.
you can slope, and you can see how many sigma they're different by. I bet it's significant.
Yeah, you could do that. But again, you're focusing on a difference of a few points here. I mean, look, this is a measurement from half a GeV to 50 GeV, and to me, it's remarkable and in very broad strokes.
I'm going to fight back because you said, haha, jet quenching, and if you look above 10 GeV, the shape looks different to me. But okay, I'll shut up now.
Okay, well, right. So okay, I take it as a interesting comment. I mean, maybe one can play the same kind of a game trying to decompose the lead into, a 10 GeV. How many of the particles could you still think of being bulk versus jet? Is that different than in P-lead?
Good point.
Yeah. Okay. Fair enough.
Could I ask a question about the same figure?
Yeah, please.
So, well, in fact, I mean, yes, there are quantitative differences, but I think it's extraordinary that, these things are they're such systems of such different size, extraordinary they fit on the same plot, right? I mean, it's just that they're even qualitatively similar. So I'm going to actually ask about the distribution below 2 GeV, and I see this factor 1.5 there you have on the axis. You didn't,
Right.
It's not what you're focusing on, so you didn't describe it, but the agreement there is truly remarkable. So is this factor 1.5 understood? Can Paul calculate it, for instance? Is there some, or is it just a phenomenological number and nobody really understands it?
Right. Yeah. So at the time we made the plot for this paper, it was an ad hoc number we put in to try to match the overall sort of vertical scale and compare the shape. However, there are people in this field who study, how efficient is the translation of epsilon n into Vn, and they actually do use multiplicative factors like this, which depend on the lifetime of the system, the viscosity, and things like that. And so I actually wonder, maybe that could be understood quantitatively from the fact that a P-led, right, system, even a 0.5 central one, probably has significantly less time to translate those spatial anisotropies into momentum anisotropies before it freezes out. And so that would not surprise me if that's kind of what we're seeing here.
Yeah, just to say the same thing, but if there's an assertion that there's a common paradigm, then you should be able to calculate that number. Right. So it'd be good to follow that up with calculations. Thanks.
Hi, Dennis. Can I ask something?
Yeah, please.
Because I noticed that you said that you are comparing to like 20 to 30% because they have the same epsilon 2.
That's right.
So may I ask, like, what type of model do you use for estimating epsilon 2 for P-led? Because that could vary a lot in different models, and you may end up comparing different centrality classes of the.
Yeah. Boy, off the top of my head, I'd have to check the paper. I assume you're asking if this is sort of a nucleon level epsilon 2 or a constituent quark level or something.
Yes, something like that.
Yeah, I'd have to check the paper. I'm sorry. Yeah. All right. Okay. Good. Let me move on. Right. So believe it or not, there's not so much in the theory literature about a simultaneous V2 and some other signature of jet quenching in the theoretical literature. But there is this one paper by Zhang and Lau that we compared to. So the plot on the left is the V2 and V3 versus PT, with the V2 in red. And, qualitatively, the magnitude of the V2 in that model agrees with what we see here. That model, and I think others that use a final state interaction paradigm, predicts a remarkably large, for example, R proton lead that you see there in the dashed line on the right. And, all of this is hard to measure in central events at the LHC. Measurements by Atlas and Elise, for example, they just don't indicate anything like the kind of the sheer magnitude of the suppression that this model thinks should accompany such a large V2 at high PT. So maybe I'll make a little diversion. So one could ask, what could jet quenching in PA look like? What associated signature could there be? So there have been measurements that use what I would say AA style observables, such as the plot on the left is the centrality integrated RP lead, which doesn't show any effect. And there are measurements based on intra-event correlations. So for example, there's a hadron triggered recoil jet distribution on the right, which places a pretty strong limit on the amount of out of cone energy loss that might be happening in the central proton lead events. So in my opinion, those are setting some pretty strict boundaries on the kind of modifications jets might experience. I think for a small energy loss, as in perhaps the bigger effect could be the softening or the modification of the in-cone part of the fragmentation. So there are measurements on my next slide. So here are some examples that look at observables like this. So there are some limits from the centrality integrated, for example, jet mass from Elise in the upper right, fragmentation functions on the bottom right. And boy, those don't really see anything either. So perhaps it's a question of we have to improve our systematic control. We can use this new, this high statistics 2016 proton lead data and tease out if there's a small effect in there. But this is probably something where it's useful to have theory guidance for what might you expect as an accompanying observable to such a large V2 in this high PT region. Okay, good. Let me change topics. Okay, so now one possible objection you could raise is, well, maybe there's some formation time argument where these high PT particles, they're not formed late. You don't really see the fragmentations proceeding as in vacuum. Maybe you don't expect a big effect. One way to avoid that is to look at heavy flavor quarks, right? Heavy flavor quarks are formed very early in the collision. They really see the whole evolution of the medium. So you can't quite make that same argument there. So this is a measurement of the collective motion for charm and bottom quarks in PP collisions. This is made by two of our postdocs, Seng-Hoon Lim, who's now a professor in Pusan National University, and Chipeng Hu, who is a postdoc now at Lawrence Livermore. So again, probably closer to where you are geographically than where I am. Okay, so charm and bottom quarks. So let me just start out by saying, I mean, heavy flavor modification is historically one of the most important signatures for understanding QGP dynamics. So from early measurements at RIC, so the plot on the left, this is a very widely known measurement of the simultaneous suppression in the RAA and the azimuthal modulation, the V2, for heavy flavor decay electrons, right, at RIC. And this is one of the papers that was one of the motivating measurements for the eta over S conjectured quantum bound. Now, of course, these heavy flavor measurements are much more sophisticated. So here's a beautiful measurement that I show you from Elise, where they're looking not at decay leptons, but at fully reconstructed D mesons. And they're doing event shape engineering. They're picking out quark-gluon plasma regions that have a different ellipticity in their shape, and they really see that if they measure the V2 for these charm mesons, it really responds in the way that you would expect to the ellipticity in the event. So the charm quarks really are thermalized and really feel the shape of the quark-gluon plasma region. So some very remarkable things happening in the large systems, since a few years ago, we started seeing some interesting phenomena in the small systems as well, if I can control my slides. So the plot on the left, this is an observation that the charm hadrons also have a pretty sizable V2 in very high multiplicity proton lead events. So I think that the plot on the left is something like 0.1% top multiplicity P lead. And at the same time, we have pretty good constraints from other measurements, such as from Elise here on the right, that the RP lead, at least the minimum bias RP lead, is not very strongly modified, maybe a little bit, but kind of in line with some expected cold nuclear matter effects. Now, these two pictures are not in principle in that much tension with one another, because the one on the left is for some exceedingly rare fraction of P-lead events, but nevertheless, you might think, what if we try to push this to an even smaller system? What if we measure charm and now also bottom in PP collisions? What will we see? So this is a measurement done in Atlas in 13 TV PP collisions. Here, the final state observable is a heavy flavor decay muons. Okay, so it's an observable which it's a final state which maybe has a little bit less direct connection to the parent heavy flavor hadron kinematics, but it's one where we have very good experimental control, allowing us to separate the charm and the bottom, for example. So in Atlas, this separation is done via two-step procedure. First, we separate what are genuine heavy flavor decay muons from other sources of muons by basically comparing the momentum we measure for those muon candidates in the inner detector and then in the muon spectrometer. There's some amount of energy they should lose passing through the dense calorimeter, and so we can see if we have a consistent picture, and if so, that's really a muon. And then we further separate those into charm and bottom hadron decay muons through their transverse impact parameter, which Atlas has very good capabilities for. Okay, we perform, again, a standard two-particle correlation analysis. And this time we do it with different selections on different selections that have different fractions of the genuine versus background muons, and then within the genuine muons, different fractions of the charm versus bottom. And we measure this with enough different points that we can sort of do a decomposition back to what the pure charm and the pure bottom of V2 are. So let me show you the results. So I show you here the V2 as a function of charge particle multiplicity in proton-proton events. And the points in blue, those are the results for the charm hadrons. And actually, we see a very big signal, V2 on the order of 5 to 10%. The data here starts at a charge particle multiplicity of 60, and that's actually something like the top 0 to 7% of PP collisions. Okay, so that's not minimum bias PP collisions, but boy, it's a significantly larger fraction of the total PP cross section compared to those first measurements in P-lead, which are some very, very tiny fraction. And we actually see no indication of a particular multiplicity dependence. So I think for me, it's easy to imagine this behavior could persist to even lower. So that was pretty surprising to see this very large charm V2, but actually, perhaps what was more surprising is the results for the bottom that you see there in red. The V2 for the B hadrons is consistent with 0. So there's a very, very strong mass effect here for the collective behavior of these heavy flavor quarks in PP collisions. I can compare these as a function of PT as well. So here is the V2 as a function of PT. So the charm is there in blue. It seems to be slowly decreasing. If I overlay that with the V2 for light hadrons there in green, boy, it sure seems like they have a very similar magnitude and PT dependence. But of course, one has to remember the decay kinematics. These are charm hadron decay muons. They're coming from charm hadrons, perhaps a GeV higher. So you could mentally shift the points a bit to the right, for example. And again, as a function of PT, the bottom hadron decay muon V2 is again compatible with 0. Now here I want to note, the bottom muon results are starting at 4 GeV because that's where we trigger an atlas. That's how much energy it takes to get through the calorimeter and make it to the muon spectrometer in the first place. So it's very hard for us with this signature to go lower. So 4 GeV bottom muons, those might be coming from bottom hadrons that are sort of 6 GeV. So could there be room for a non-zero BV2 lower than this? Perhaps, but certainly in this kinematic range, there's a very stark difference between the charm and the bottom. Let's see. So how do we understand this? Well, as I mentioned in final state interaction models, and certainly for Langevin-based models of heavy quark diffusion in the QGP, again, one gets a azimuthal anisotropy in tandem with a modification of the PT distribution, right? In those models, it's impossible for these heavy objects to be so strongly redirected an angle that there's no visible effect in their PT distribution. So we actually have a recent atlas measurement of the overall charm a cross section in PP collisions for charm goes to muons. It's compared here to faunal calculations, and basically in the PT range where we can measure this azimuthal anisotropy, I mean, there's very little room there's little room, I should say, for a big effect, at least within the status of the data to theory comparisons as they are. So one could think about other possible mechanisms, for example, initial state mechanisms. There are calculations out there in the literature where a color glass condensate initial state framework can describe the flow that we see for charm. So there's an example here in proton lead collisions. And it similarly predicts kind of a non-trivial mass effect between the charm, which is there in the teal, and the bottom there in red. So I'd be interested, what would this kind of model predict in PP collisions, where, remember, it's a CGC calculation, so they don't get the benefit of that 8 to the 1/3 enhancement in the saturation scale. So would you still expect to see the magnitude of the azimuthal anisotropy that we see in P-lead? Okay, good. Maybe let's, one more comment. Boy, this difference between charm and bottom quarks actually seems to be pretty important everywhere. Here's yet another measurement of the V2 and the V3 for charm and bottom separated muons, also made by Seng-Hoon and Shipong, but now in lead-lead. So the plot on the left shows you the difference in the V2 between charm and bottom. There's a very big effect there in the V2 and also in the V3 and the plot in the middle. And this shows up in other ways. I mean, even though the way that that Corconia acquire a V2 is a bit different than from how open heavy flavor acquires a V2. There's, for example, these interesting measurements by Elise and then now also by CMS that, you know, there's a large flow for the J psi, but not for the upsilon. And so those are CC bar and BB bar bound states respectively. So I wonder if that's not a coincidence. Somehow in all kinds of systems, small and large, the difference between the C and the B seems particularly valuable and sort of showing you where the flow starts and stops. Okay, maybe I don't know if there's questions here. I have one more topic, but it's going to move quite a bit away from heavy flavor. Okay, I'll go on. So the third and final measurement, this is a measurement by our graduate student Blair Seidlitz. He is actually on track to finish his PhD this year. So he's a very excellent, productive student in case you were interested. And I'm going to show you the final results from this measurement where Blair is searching for collective phenomena in photonuclear collisions, which are pretty exotic. Sort of system quite different from proton-proton and proton-lead. So first of all, maybe let me put this in some broader context. In a final state interaction picture, it's not enough to just have a lot of multiplicity to give you an azimuthal anisotropy. In these kind of pictures, an azimuthal anisotropy really comes from an intrinsic transverse geometry. You have to have something there that's elliptic, there's a third order eccentricity or something in order for the final state interactions to translate that into azimuthal anisotropies in the momentum space. And actually, not only do you have to have an intrinsic geometry, but it's got to be an intrinsic geometry that's persistent across rapidity. Okay, so that there's a preferred direction of particles kind of globally all over the event in rapidity as well. If you just have sort of localized fluctuations in geometry, that's not going to generate a global V2 or a V3 or a V4. So a few years ago, some of us in the Colorado group and then collaborating with Jiwei Lin did a study of whether one could expect this kind of phenomena in E+E- collisions. Okay, so we modeled these in AMPT as electron-positron annihilation briefly creates this Z, which decays to back-to-back quarks, and we stretch an AMPT color string between the quarks as if they were receding beam. We do the analysis around that quark axis. Okay, so this string is going to tunnel out. It's going to produce partons. AMPT has some particular way of doing that. And if you turn on parton rescattering, the partons will interact and will change their trajectories. But because it's a single string, it's got no structure in the transverse plane. It's a 1D object. There's no particular preferred direction for the partons to scatter to. So you're not going to get a long-range ridge. On the other hand, we took a kind of fictitious case. This wouldn't happen in reality, but if you just do the thought experiment with me, if instead of one color string, what if you had two color strings that were separated by something on the order of a Fermi receding in the same direction? In that case, both of those strings are producing partons, and the partons that are moving between the strings are particularly likely to scatter to a transverse direction. And so now, in the transverse plane, you've instituted an overall global geometry, and so turning on particle rescattering, as you can see there in blue in the correlation function on the right, really will generate this symmetric ridge with a near side peak. So again, the overall story here, it's not enough to have multiplicity. You've got to have some kind of transverse geometry if you think final state interactions are the picture. So I think as many people here know, there's been kind of a cottage industry of people now digging into various archived exotic collision systems and looking for these kinds of effects there with two-particle correlation analyses. The plot on the left, this is an example from a study in E+, E- done a year later, where basically they don't observe anything like a near side ridge. They set some upper limit on the possible magnitude of a V2. And again, to me, in my argument, that's expected if you think final state interactions are what's causing the collective phenomena, because there's no long range geometry in E+, E-, so you can't generate a V2. There are measurements also in EP collisions. So I think by Zeus is a nice publication. Here's some 2D correlation functions. Boy, they look quite different from what we see in the hadron-hadron collisions, and the conclusion there is, again, they don't really see anything compatible with collective effects. So given that I just showed you that we have non-zero V2 and V3 and PP and PA, but we don't really see anything in EE and EP, the motivation here is to go to a system that schematically is kind of trying to fill in the middle here, and to look at photonuclear collisions, okay? So these photonuclear collisions, these are cases where the two nuclei pass each other, and one of the nuclei emits a photon which strikes the other, okay? That struck nucleon then goes on to fragment, produce particles, what have you. In my example event display here, that's the nucleus traveling to the right, producing particles that way. The other nucleus which emitted the photon continues on down the beam pipe, mostly unaffected. So there's no particle production on that side. So our graduate student Blair, so he really devised and commissioned a trigger to be able to select events with this overall topology that have a high multiplicity, so we can do this measurement. There's a very interesting playground for physics that's harder to access in PP and PA collisions. It's the photoproduction limit of DIS on nuclei. So if you like, you can think of the gamma A as an opportunity to do a little bit of EIC-like physics before there's an EIC. So to me, that's pretty exciting. Okay, let me just tell you briefly, technically, how we're selecting these events before I get to the results. So we want to quantify the degree of the one-sidedness. We want some variable that allows us to separate these one-sided gamma A topologies from the typical peripheral lead events. We do this via a sum of rapidity gaps. So we look for events where there's large gaps between produced particles on one side. We add up those gaps. We also require significant deposits in a 0-degree calorimeter from the neutrons on one side, but not on the other, okay? The plot on the right shows you, this is a scatter plot of events with the size of the gap on the x-axis and the charged particle multiplicity on the y-axis, and basically our signal photonuclear events are here in the bottom right. So those are the events with a large sum of gaps on the photon going side and then a one-sided ZDC signal. We can characterize what these events look like physically. Where are the particles? Where are they going? The plot on the left shows you the multiplicity distribution for the gamma A events there in black. It's very, very, very steeply falling. It's difficult for these events to produce a large amount of particles. It's just a photon striking the nucleus. And that's compared to what's shown there in red is sort of an anti-selection. So picking out what we think are really peripheral dominated events there in red. And those are a very different multiplicity distribution. We can look at the DND eta, at the shape of the event in pseudorapidity for these gamma A events. And perhaps unsurprisingly, they are very asymmetric. They are peaked towards the direction that the struck nucleus is going, and that shape changes very little over a pretty broad multiplicity range. So between the two of these, this is sort of reminiscent to me of PA collisions, another example of something very little hitting something very big. Okay, we can perform a two-particle correlation analysis in this system as well. The figure on the left shows you this correlation function in the delta phi, delta eta space. This looks broadly pretty similarly to what we observe in hadronic proton-proton or proton-lead collisions. And again, following this set of standard techniques, we can systematically decompose the correlation function into a non-flow component and a modulated a component that you see there in the bottom panel. So again, we are able to pick out with enough work an enhancement here on the near side and a mostly symmetric ridge in this correlation function. We translate that into a V2 and a V3. So let me summarize the results here for you on this slide. The plot on the left shows you the V2 for photonuclear events. Those are the dark red points there, and the V3, the dark blue points, as a function of N charged. Okay. The PT integrated V2, as I'm showing it to you here, seems to be about 4-ish%. And multiplicity independent, although we only got 3 points with non-trivial uncertainties, so hard to say too much. We compare them, the open points there are the analogous V2 in proton-proton and proton-lead, so those are a bit higher than what we see in the gamma A. And then the V3, it's hard to make too strong of a statement. We can also look at the PT dependence of the V2. That's the plot here on the right. So the V2 in these photonuclear events is shown there in the dark red. Boy, the uncertainties are large. We see something compatible with a rise, similar to what we have observed in PP collisions there in the open squares, or the stars in P lead. But we start to lose control at higher PT because the non-flow effects are just getting to be so darn big. So it's hard to say too much, but certainly qualitatively compatible with PP. Okay, so I've shown you that there seems to be this collective behavior in the photonuclear events as well. So how do we understand those? Actually, I think the photonuclear is an excellent testing ground for understanding the interplay of initial and final state effects, because it's a system with basically the most different initial state from any of the others, right? The photon is sort of extremely different, or a proton or a nucleus or something like that. So there's already a calculation there on the market, again within the CGC framework, where the authors basically argue that, yeah, in this kind of picture, you really do expect to see a V2 with this approximate PT dependence and magnitude in the gamma A collisions, and that this is going to be a benchmark for signals that we might expect at the EIC. However, I wonder if there's also a possible explanation in the final state paradigm. So we know, I think we've known for a while, that at high energies, the prevailing paradigm to describe these photon-induced interactions is something called vector meson dominance. So the idea here is the photon can very readily fluctuate into something with the same quantum numbers, a meson, commonly a rho, for example. And so particularly in the events where you produce a lot of multiplicity, these interactions may actually be proceeding as rho nucleus collisions. Yeah. And so I wonder, is there anybody out there who's brave enough to try to really mock this up in a hydro picture? You'd have to model the transverse spatial structure of the rho. You probably have to use a 3D hydro because the system is most likely very not boost invariant, other complications like that. But I wonder what such a simulation would predict for the V2 in these photonuclear collisions. Okay, so let me bring it back to my concluding slide. So remember, the question I asked in the beginning was what can stop the flow? Can we find things and systems which don't flow? Actually, from the 3 examples I showed you, we have mostly failed in our quest. We've mostly failed to find what can stop the flow, right? I showed you a measurement where we see an azimuthal anisotropy that seems pretty dang robust for up to 50 GeV particles in a pretty broad fraction of proton-lead events. I think the key question there is, if this is coming from final state interaction, where's the accompanying jet modification? If it's coming from the initial state, how can something in the initial state persist up to such a high PT? I've shown you a measurement of charm and bottom heavy flavor quarks separately in PP collisions, where actually we do finally see something. The bottom quark seems to refuse to flow, at least in the kinematic range where we've measured it. So good, that's at least some anchor point to help us delineate between physics mechanisms. And finally, I've shown you measurement in photonuclear events. And so this, again, as I mentioned, I think because it's so different from the others, it's a particularly interesting test bed for, is this a test bed for the kinds of phenomena we might see at the IC, or is there perhaps a more conventional explanation in terms of final state interactions arising from some underlying geometry? All right. Well, let me thank you for your attention. I'm very happy for questions.
Great, thanks, Dennis. I see Peter already has his hands up.
Dennis, thanks for a great talk. Really beautiful data. I want to propose a possible solution to your bullet number 1 here, which kind of runs into trouble in bullet number 2, but let me try it anyway. And it's a very trivial observation that what we compare is hadron suppression, RIA, or recoil suppression at fixed PT for different systems. But in fact, the slope of the hadron spectrum is much steeper than the slope of the jet spectrum. So a small amount of energy loss may actually exhibit itself in a hadron suppression and not a jet suppression, but the same is also true for V2. V2 is an anisotropy, and it may be, and this is just pure conjecture, I have no calculations, it may be that a small amount of energy loss can produce a finite V2 in hadrons, which would be very hard to detect in jets simply because the shape of the spectrum. Now, as you were talking, I was trying to figure out whether that's consistent with your heavy flavor results, and I kind of concluded it was not. But let's ignore that for the moment. What's your comment about sort of inclusive hadrons versus inclusive jets?
Peter, boy, I think we're up against a wall, and so anything goes. I mean, I would love to see detailed, dihadron IAAs. I think that's totally appropriate at this point. Yeah, I agree with you. Your general point.
Well, actually, so let me propose that the way to figure this out is, you very, very carefully and rigorously just show data and compare data, but I think we can't escape calculations. I think what we need to do is try to calculate both within some appropriate framework. Could be Jetscape. It could be Jetscape is a good candidate. There are, I'm sure, others, but I think at this point, given rather basic differences, I mean, the shape of the spectrum is just, it comes in, we can't escape that. I think we have to sort of appeal to a third party, namely a calculation, to see if we can come up with some kind of, consistent picture. That's actually the only way I see at this point. The data are quite strong in many sectors, and these heavy flavor are really spectacular. And in order to get consistency, I think, or identify where the contradiction lies, at this point, I think calculations are inevitable.
Yeah. So I think I'm in broad agreement with you. I could also say, I mean, I'm focusing on these 3 particular Atlas measurements, but another way to sort of increase the steepness of your spectrum in a qualitatively different way is to move from the LHC to RIC. Right. I mean, it might be that maybe this is also something where there's a particular physics benefit in new measurements in DA and PA, but at the hadron level.
Yep, I agree.
Okay, next, sorry, I'm going off Zoom here. Torieri.
Hi, thank you very, very much. It was a spectacular talk. I'm glad it was recorded. I'll get the YouTube link. Just as a sort of comment about the previous discussion, what is nice about it is that yes, calculations are great, but you go at the heart at some very qualitative issues, in my opinion. Qualitative. I mean, V2 at low PT is caused by pressure gradients. V2 at high PT is caused by tomography. So one is a gradient, the other one is an integrated length.
But they both come from the same geometry. That's what trying to stress.
Well, a geometry of gradients and a geometry of an integral of a function and the gradient of a function are different things, unless that function is an exponential, unless it's really fine-tuned. So I actually, I mean, until there is a significant, I mean, perhaps this, what Peter mentioned could serve as something, but it's the RPA, which is consistent with one. It's not RPA of jets. While RPA of particles is consistent with one, while V2 of the two have a constant ratio, I mean, this is, I won't believe anything called state of the art, which doesn't also explain this.
Yeah.
And the same thing for heavy quarks. The fact that the mean free path of anything goes as m/t is something which is in every statistical mechanics text. It's in absolutely every statistical mechanics text, and this is, at least, it seems to be falsifying. I mean, I just want to say something that, you know, I mean, in the philosophy of science of Thomas Kuhn, you have paradigms and you have puzzles which put progressively paradigms in crisis. And this is a potential puzzle. I mean, I'm at a loss also to even qualitatively interpret this.
I take that as a comment. I mean, right. To me, I think some of these results taken together, they really push what was a tension in previous data to sort of a breaking point where you really can't ignore how can these high PT things flow so much. Yeah.
Okay, so next we have Au+Au.
Oh, hi, thanks for the talk. So I'm just really interested in this last point. So basically the anisotropy in the photonuclear events. I've never seen this before. Thanks. So if you can go back to that results. I missed it. So what is the rapidity for this particle that you use to compute V2 in this gamma A events?
Yeah, so the measurements are done in the, maybe I can, is it better to show here? Well, right, they're done in the central tracker, which goes from an eta of -2.5 to +2.5. And there are some, maybe this is better here on the right. And there are some complications in that, because of course the energy of the photon is much less than the energy of a nucleon in the nucleus. So the whole system is boosted a lot in this direction. And so there are some kind of funny issues with, we're doing two particle correlations, but in kind of a back half of the event, and things like that.
Because you have this very boosted or center of mass frame. I've just try to picturize that which side you're measuring. Are you measuring the fragments of the nucleus, or are you measuring the fragments from the?
No. In the photon fragment side. In fact, that's one of the reasons we're using this kind of complicated sum of gaps measurement, is because we saw some events where there's a big gap, but just maybe a few localized particles that are presumably from a photon remnant. And so we did not want to cut those out because those are actually legitimate gamma A processes. So we're looking at sort of more the photon fragment half of the event. Yeah.
Okay, Xinyan.
Yes. Dennis, thank you for the nice talk. I think you already have mentioned that when you trying to calculate this V2 with high PD trigger and also associated particle correlation, you also have to you have selected the PT range of the associated particle, right?
Yes, right.
And how high that PT can go?
Right. So let's see. I think we I can't remember if we pick some restricted range or if we just
here you can.
Here it is. Yeah, sorry.
Yeah, it's 2 to 3 GeV, right?
So the plot on the right shows you what you get for the V2 of the trigger particle using different associated PT ranges. So yeah, right. For the nominal, we just use all particles above 0.4 GeV.
Yeah, about
with
0.3.
associated.
But then, so this also this two particle has to have rapidity gap, right?
Yes, yes,
Yeah,
that's right.
I just wondering that how high PD can go. I mean, in principle, if the associated particle can also go to like 10 GeV,
well, right. Boy, a 10 GeV particle correlated with a 10 G part. I mean, the digest contribution is going to be huge. That's the hard part. It's really helpful to have one of the particles be from the bulk. Yeah.
Yeah. Well, those are sort of jet, back-to-back jet, and in principle, they should also have an angular correlation.
Yes, but it's not the one that we're trying to pick out. Right, we're trying to pick out sort of the orientation of this high PT particle with respect to the bulk event plane, as it were.
I understand that. Your bulk essentially is, I mean, you are just doing two particle correlation, right? You're not doing you're not doing cumulant, like.
That's right. So I interpret the results as a V2 for high PT particles, but technically what we measure is the fact that the direction of high PT particles is aligned with the direction of the overall soft particles. That's technically what we measure.
Yeah. Is it possible for you to do like cumulant, like for example, using 4 particles, but one of particle is high PT, the other 3 are like low PT? Is that possible?
I think it's technically possible, but why? I guess I'm curious what you think it would show that we.
Well, this essentially is this can differentiate the true collective flow versus like a color glass condensate model. In the color glass condensate model, they are just have 2 particle correlation. It's because they have initial scattering and with large rapidity gap because of some kind of interference. So they have some kind of angular correlation. But that will not probably hold on if you go to multi-particle correlation.
Yes. Yep. Okay. Yeah. Very well. Yeah. I'm aware of the point. Well, what I can say is this factorization test that we've done here. If the source of the correlation is is really a 2-particle, not a global single particle thing, you would not necessarily expect this factorization test to work. The factorization test shows you that the V2 of particle 1 and particle 2 equals V2 of particle 1 times V2 of particle 2. You could separate them into single particle modulations. So that check is already, in my opinion, strong evidence that it's not that kind of initial state effect. But yeah, it would be interesting in principle to do multi-particle cumulants as well.
I mean, this test is also done for like PLAD?
Yes.
I see. Well, this, there's contradiction of puzzling between whether V2, and the suppression, they are really, coming hand in hand, right?
Yeah, I guess for me, if somebody tries to raise an initial state as a possible explanation for this, I mean, for the low PT, heavy flavor, the photonuclear, maybe, but I mean, 50 GeV particles, I mean, how could they possibly? Those partons are so localized; they don't know anything about what's going on around them. How could they possibly care about the initial state?
These are just like the just initial scattering. They don't need just they just have multiple scattering, like 1-2 scattering. Is in a way is very similar to the picture that what you mentioned. Paul or Magica did is what happened if you have just 1 scattering. In the final state, right? And this could also be a possibility that you have just 1 or couple of scatterings, but without energy loss, because the scattering can deflect your angle that can give you some kind of like V2, but with no significant energy loss. That is another possibility.
Yeah, well, maybe I'll mimic Peter and say, I'd love to see that really concretely worked out in a theory.
Yeah.
In a theoretical framework.
Yeah. Anyway, I think this if you put all this together, there is really, I guess there is some kind of underlying common physics magnets among all those, like whether it's high PD V2 or heavy flavor V2 or diapside V2.
Perhaps, yeah.
Yeah. Well, thank you very much.
Whatever it is, it would have to really fit the particular pattern of this flows, this doesn't, yeah.
Yeah, I mean, definitely we see that this current data does not allow any significant amount of energy loss. That's for sure, right?
I think that's right. Yeah, or at least certain types of commonly envisioned.
Yeah.
Okay, great. Thank you. Well, thank Dennis again. I don't see any other hands, so nope, nothing else. So thanks again, Dennis. I don't know if you've been asked to send your slides yet.
Yeah, please send us your slides.
You can send them to me or to Shinyan. That's fine. So we'll put those up on the website, and we'll put this video up on YouTube.
Okay. Thank you, everybody. It was a pleasure.
Okay. Thank you very much.
Again.
All right. In person next time, I hope. Yeah.
Yeah. Bye-bye.